least from today, right now, you will be done with this course. All right. So today we're going to continue talking about relativity. Are there any questions quickly before we get back to that? I don't think so. All right. So last time we had started talking about how in order to satisfy these postulates of special relativity, that all laws of physics are the same in all inertial frames, and then the speed of light in a vacuum is the same in all inertial frames, regardless or independent of both the speed of the source of light and the speed of the observer. In order to satisfy these two postulates, we have to mess with time and space. So first we said that different observers will experience time differently, or you will see time ticking slower in a moving reference frame that's moving relative to you at some speed close to the speed of light. If you're not moving close to the speed of light, then you don't usually see much of a time difference. We can agree on time. When I'm walking across the room and only at a couple meters per second, right? The time dilation in my frame, my inertial frame, is not considerable compared to your inertial frame. So you have to travel it close to the speed of light for this square root in the denominator of time dilation to be something that is considerably less than 1 and therefore making delta t larger. There's also length contraction, right? So if you have an object traveling with some velocity, then it will be shortened along the direction of that velocity from the relative perspective of someone at rest. And so we illustrated that last time with this slide of 2 different train cars and Trillium, who is standing here with v is equal to 0. So she's standing on the ground, v is equal to 0. One train car at the one at the top also has v is equal to 0. So it's at rest in her frame of reference, and she measures the length of that car to be L rest. But the other train car, which is an identical train car, is traveling past her at 8/10 of the speed of light, and so she will measure it to have a shorter length. And that's what I've illustrated here on the slide. And the length that she will measure is L equal to L rest times square root of 1 minus v squared over c squared, where v squared in that equation is the speed of the train, 0.8 c, 80% of the speed of light. So she's going to measure a shorter length. All right, let's do a question. Let me give you 3 minutes to work on this. LC stands for learning catalytics, not length contraction. And not inductor capacitor. Still got a minute and a half left. So it seems like this is not possible, right? But with special relativity, it would be possible. Seconds. Okay, I'm going to stop it there. The correct answer was, had the wrong arrow, 0.6 c, 6/10 of the speed of light. So let's work out how you actually get that answer. So we want the length of the arrow to be 4/5 the rest length of the arrow. And then we can also use this equation to figure out what that speed must be then. So this is the length, L rest times the square root of 1 minus v squared over c squared. Well, L rest cancels, and so then I have 4/5 is equal to the square root of 1 minus v squared over c squared. I can square both sides and get 16/25 is equal to 1 minus v squared over c squared. I'm going to add v squared over c squared to both sides, subtract 16/25 from 1, which is going to give me v squared over c squared is equal to 9/25, and then take the square root of both sides to give me v over c is 3/5, or v is equal to 3/5 c, which is equal to 0.6 times the speed of light. So if you travel at 60% of the speed of light, your length will be shortened by 20%. All right. So there are some interesting results that come from time dilation and length contraction. And so let me show you this to begin with on a slide. Then we're going to come back and do out this example to figure out what's going on here. So this is something called, eventually, when the input goes away, the twin paradox. So there are two twins. Twins are born at the same time, so they're the same age, right, on Earth. And one twin stays on Earth with, we're going to call that v is equal to 0, even though the Earth is rotating, right, and it does have motion relative to things, and it's traveling through space. Well, we're going to assume that v is equal to 0. The second twin gets on a spaceship, traveling outwards at 8/10 of the speed of light for some amount of time, for some number of years. And then twin 2 turns around and returns back to Earth on the spaceship, still traveling at 8/10 of the speed of light. When twin 2 returns to Earth, twin 2 will be younger than twin 1. And now remember, we had an example previously, or we did a learning title discussion previously, where I asked you if Zaphod is traveling past Earth in his spaceship at half the speed of light, and Trillium is on Earth, and each of them views the other one's clock, right? We said that each of them views the other one's clock traveling slower, because that's a symmetric situation. You have one reference frame is traveling at v in the opposite direction, or v relative to the other reference frame. And so from the perspective of each observer, it's symmetric. It's the same thing. Each of them sees the other one traveling away at half the speed of light. And so they both see each other's clocks ticking slower, right? But this is not symmetric. This is not symmetric because twin 2's trip is different than what twin 1 experiences. Twin 2 has to accelerate up to 8/10 of the speed of light. So she spends time in a non-inertial frame, in an accelerating reference frame. And so that's different than twin 1. And then in order to return back to Earth, she has to turn around. When you change the direction of your velocity, or if you slow down and turn around and come back the way that you came, that's acceleration as well. Right? So if you travel along a curve, that's acceleration. Or if you slow down and then come back in the opposite direction, that's also acceleration. That's an accelerating non-inertial frame. And so twin 2 has spent time in non-inertial frames a couple different times. And that's what's responsible in the end for the fact that she actually ends up being younger when she comes back. Okay, but we can work this out with special relativity mathematically. So let's do that. So let's just write down twin paradox in this example as well. So twin 1 remains on Earth. Feels kind of cool in here today, right? Yeah. So there was like some sort of technical issue with the building. They emailed us about it. They're working on it. So it is a little bit cold for the time. Hopefully they'll get that fixed before finals. So twin 2 travels, let's say, 4 light years at v is equal to 8/10 of the speed of light, 80% of the speed of light. So the full trip, because they're traveling 4 light years out, is 4 light years out and 4 light years back. So a total of 8 light years, right? Then they turn around, right, come back. So by the way, we haven't talked about light years, but I think you've probably heard of light years before, right? A light year is the distance that light travels in a vacuum at the speed of light in a vacuum in 1 year, right? So you take that 3 times 10 to the 8th meters per second that we use for the speed of light, 2.998, but basically 3 times 10 to the 8th meters per second. You multiply that by the number of seconds in a year, which is 24 hours in a day, 60 minutes per hour, 60 seconds per minute. How many days in a year? 365? Not quite. 365 and a quarter. It's actually 365.24402, but don't worry about those decimal places. That's how we have leap years every 4 years, but then every 100 years we don't. Except on, there's other rules. But we have to add a day every 4 years, right? So it's close to 365.25. Number of seconds in a year is about 31 million. Okay, it's about 31,500,000, something like that. All right, so you multiply that by the speed of light in a vacuum, 3 times 10 to the 8th meters per second, you get the distance in 1 light year, right? And distances in astronomy are usually measured in light years or in a different unit that astronomers use called parsecs, which is 3.26 light years, because the distances are so far, right? We don't usually have to worry about distances that are that large. Okay, so let's start with twin 1. From twin 1's perspective, the trip takes 10 years. It's 10 years because twin 2 is traveling 8 light years at 8/10 the speed of light. Right? So if you divide 8 light years by 8/10 the speed of light, you get 10 years. Okay? And we're not going to worry about the period where she's speeding up and slowing down. Let's imagine that that just takes a short amount of that 10 years. So it's basically a trip at essentially constant speed, 8/10 the speed of light. But she also sees time ticking slower for twin 2. And so we can use time dilation to figure that out, to figure out what she sees for twin 2, or what she sees happening with the clock on twin 2's spaceship. Okay, and so that's time dilation. So delta T1, which is the amount of time that passes according to twin 1, is equal to delta T2 divided by the square root of 1 minus v squared over c squared. And delta T2 here is the time that twin 1 sees ticking off on the clock of twin 2's spaceship. Okay? So this is the proper time, and then this is the time in twin 1's reference frame. Okay. So we're trying to solve for delta T2. This delta T1 is the 10 years. Okay, so if we do that, we get delta T2 is equal to delta T1 times the square root of 1 minus v squared over c squared. And so if I put in my values, delta T2 is 10 years for delta T1 times 1 minus, and there here's where you have to put in 0.8 times c, speed of light, quantity squared, divided by c squared. And this c is going to cancel with this c squared. And so what do we end up with? Well, we end up with 10 years times the square root of 1 minus 0.64, which is 0.8 squared. That's 0.36. And the square root of that is 0.6, so I get 6 years. Calculate that out. So, again, twin 1's on Earth. They're looking at a clock on twin 2's spaceship. And in the 10 years that the trip takes, twin 1 sees 6 years tick off on the clock of twin 2's spaceship. All right. Let's do it from the perspective of, so for a 10-year trip, let's say they were 20 when twin 2 left. That means that when twin 2 returns, twin 1 will be 30, and twin 2 will be 26. So there'll be 4 years difference in their ages. Okay, let's do it from twin 2's perspective. From twin 2's perspective, the distance is shorter. That's because she's traveling at 8/10 of the speed of light, right? But this 8 light years that twin 1 measures, that's the length at rest in her reference frame. Well, in the reference frame of twin 2, she's traveling relative to that length, along that length. And so that length appears shorter because it's relativity, right? She's traveling relative to Earth, but she could also think of that, flying past her spaceship and at 8/10 of the speed of light, and so it appears shorter. So in other words, not 4 light years for her. So let's figure out that length. Well, length is L rest times the square root of 1 minus v squared over c squared. And the rest length is 4 light years, right? That's in the reference frame of twin 1. But for twin 2, who's traveling at 8/10 of the speed of light, that's 1 minus 0.8 c squared over c squared. We figured out that this term in the square root is equal to 0.6. So if I have 0.6 times 4 light years, I get 2.4 light years. So from twin 2's perspective, it's a shorter distance that she's traveling. So therefore, she experiences the trip taking delta T2, which is just the distance, 2.4 light years, multiplied by 2, because that's the trip out and back, divided by 0.8c, so this is 4.8 divided by 0.8c. When I divide light years by the speed of light, I get time, and that is 6 years. 4.8 divided by 0.8 is 6. So they agree. Yes.
So if you talk about the speed of light, you know what you're talking about?
Yes. You cannot though. We're going to talk about why that is later. Okay. So light can travel at the speed of light, but you, somebody with mass, cannot. We're going to talk about it later. Okay. All right. So this seems weird, right? That time has passed differently for twin 2 than it did for twin 1. But remember what I said on the slide. This is because their trips are not, their experience of time is not symmetric. And twin 2 has spent time in accelerating reference frames 2 times in order to accelerate up to 8/10 of the speed of light, and then and then accelerating again in order to turn around and come back. And that's responsible for why time has passed more slowly for her than her other twin, who's now 30, and she's only celebrating her 26th birthday. Okay. Okay, so we saw previously that you can translate between reference frames using the Galilean transformation. It is pretty straightforward for translating between one reference frame and another, right? If I'm walking across the room, I'm in an inertial frame, you're in an inertial frame, I have a velocity relative to you, and then we can just do a simple subtraction to translate from one inertial frame to the other. It's a little bit harder in relativity because of the fact that both time and length have changed. And so we have to use a different transformation. We can't use the Galilean transformation, but instead, there is a different transformation that works, and that is called the Lorentz transformation. So x prime is equal to x minus v times t, which was the same as what we had in the Galilean transformation, but now we have a factor of the square root of 1 minus v squared over c squared on the bottom. So this is for relative motion along the x direction. Y prime is still y, z prime is still z, and t prime is equal to t minus v over c squared times x divided by the square root of 1 minus v squared over c squared. Sorry, I ran out of space at the bottom of the page. Okay, so this is 2 different reference frames, right? We have a reference frame with x, y, z, and t, and then we have a second reference frame that's moving relative to the first reference frame with speed v, or with velocity v, that has x prime, y prime, z prime, and t prime. Okay? And so these 2 different observers will experience space and time slightly differently. So let me write down, before we get to the next page, I'm sorry. If V over C, now let's keep it like this. If V over C is very small, as it is for us in day-to-day life, or essentially equal to 0, then Lorentz transformation reduces to the Galilean transformation. Let's show that. It's pretty straightforward, but x prime becomes x minus v times t divided by the square root of 1 minus v squared over c squared, but this is basically 0. And so on the denominator, I have the square root of 1, and so this just becomes x minus v times t, which is what the Galilean transformation gave us. And y and z prime, y prime and z prime are the same as what we had before in the Galilean transformation. And t prime, which is equal to t minus v divided by c squared times x divided by 1 minus v squared over c squared. So this again is 0. So again, I'm dividing by 1. So I have t minus v over c squared times x. But if v over c is essentially 0 for small v over c, then v over c squared is even closer to 0. So this second term goes away as well. So this is essentially 0. And so that's just t. So I'm going to make these little swigglies approximately equal to t. Approximately equal to t. So this basically just reduces to the Galilean transformation when v over c is very small, which is good, because that way it's giving us something that is more general. So the Lorentz transformation contains the Galilean transformation within it, right? It works out to the same thing for very small values of v. So you can translate with position, x, y, z, and time, t, but you can also translate velocity from one reference frame to another when v is close to c, and that's the Lorentz velocity transformation. And that is vx prime is equal to vx minus v divided by 1 minus v over c squared times vx. And it's a little bit tricky to keep track of what all the v's are here, so let's label what each of those are, or let's define what each of those are. So we have an observer in the S reference frame, and they see a velocity vx of some object, right? So let's say that's you in your seat, and you see fly across the room, okay? So you're seeing that object have some velocity vx. There's another observer in a second reference frame, s prime, and they're seeing vx prime. Let's say that's me. My reference frame, s prime, is moving relative to your reference frame. So I'm, say, walking across the room, and I'm seeing the same fly moving across the room, but I see it moving at vx prime. Okay? So you're in one reference frame, you see the fly moving at vx. I'm in another reference frame, I see the fly moving at vx prime based on how I'm moving relative to you, which is s prime relative to s is v. So that's the speed at which I'm moving across the room. Okay? Hopefully we get it all kept track of everything. So really what we're doing is we're finding Vx prime based on observations in S, or measurements in S. Right. There's also an inverse. Lorentz transformation. And that's if you're in S prime and you want to find the velocity of something in S. And so that is Vx is equal to Vx prime plus V divided by 1 plus V over C squared Vx prime. So it's a very similar expression to what we had up above, but the negative, the subtraction becomes addition. And this one is finding Vx based on observations in S prime. So in the first case, you would use the first Lorentz transformation. So this is, again, you're the person or observer in S. I'm in S prime walking across the room. Okay. And in the first case for the Lorentz transformation, you're trying to figure out what velocity Vx prime do I measure for the fly. Okay, based on the velocity of the fly that you measure in your reference frame and the velocity of me relative to you, which is V. So this is the velocity of the fly in your reference frame, this is the velocity of me, and this is the velocity that I measure for the fly in my reference frame. Right? And of course, I'm moving much faster than just walking across the room. And then this is the other way around. This is if I was trying to measure how fast the fly is traveling in your reference frame, which is Vx, based on measurements in my reference frame, plus how fast you appear to be traveling relative to me, which is V, right? Because that's our relative motion. Okay, I know, it's a little bit tricky to keep track of this, but let's do a quick example of this. We're gonna go back to an example that we had on the slide before. So previously, we had an example like this, where there was a spaceship that was traveling at half the speed of light. And then over here, we had a red laser. And that red laser is firing the laser at C in the reference frame, in the frame of reference of the laser. Right? Okay. So there's two reference frames. There's the reference frame of the laser. We're going to call that S. There's the reference frame or the inertial frame of the spaceship. We're going to call that S prime. And then there is the speed of the laser for the observer in S, which is Vx. All right, and then the speed of S prime relative to S is V, which is the half 0.5 c. So V is equal to 0.5 c. So that's the relative velocity between these two reference frames, right? We're assuming we're in the reference frame of the laser, and the spaceship is traveling in that direction, right? We know that Vx, in this case, is equal to minus c. Usually we take the positive direction to be to the right, so if this laser is firing to the left, it has a velocity to the left. You still have to obey vector directions when you're doing things like this. And so we want to know, what is the speed measured by the person on the spaceship of this laser beam coming towards them? And we said previously that the speed of the second postulate for special relativity says that the speed of light has to be the same for all observers, regardless of whether the source is moving or the observer is moving, right? So they should see C in the end. And that's what we're looking for. We're looking for Vx prime. So this is the speed of the laser beam measured on the spaceship. Okay, so let's work that out with the Lorentz transformation. So again, we're going to take this reference frame as our S reference frame. This is our S prime reference frame. So we're trying to find Vx prime. So we'll use Lorentz transformation that we wrote down above here. So Vx prime is equal to Vx. That's the speed of the laser in the reference frame of the person who fired the laser, where it's at rest. So that's minus c. Minus v, which is 0.5 c, divided by 1 minus v, which is again 0.5 c, divided by c squared, and then multiplied by multiplied by vx, which we said again is minus c. All right, so let's work this out algebraically. So I'm going to take out a common factor of minus c. So this is minus c times 1 plus 0.5 divided by, on the bottom, well, this c divided by c squared, or this c times this negative c gives me minus c squared, divided by c squared gives me minus 1 times 0.5 is plus 0.5. So I have 1 plus 0.5. And so they measure minus c. So the person on the spaceship measures minus c as well, right? Same as the observer in rest frame of the laser. So that's good. That fits with the second postulate, that the speed of light in a vacuum is the same for all observers. Right? So there you go. Okay. It seems strange. This seems like some sort of mathematical magic trick that we pull in order for it to work out to c. If it was a different velocity other than the speed of light, c, then you would get a different velocity for the different observers. Okay? But it's always going to be less than c, right, for something that is not traveling at the speed of light. But you get a different velocity for different observers. That's always less than c. That comes out of either the Lorentz transformation or the inverse Lorentz transformation. All right, so we've messed with space and time. Let me ask you to think back to physics 1 for just a second. What's the equation for momentum? P equals mv, right? Momentum is equal to mass times velocity, right? And somebody else, what's the equation for kinetic energy? We've used that in this class too, I think. 1/2 mv squared, right? So each of those equations has a velocity in it. Velocity is just length divided by time, right? Okay, in terms of the units. Well, but in relativity, we mess with length and time. So when we're dealing with something like kinetic energy or momentum in relativity, we have to make some changes. All right. So the work energy theorem said that the net work done on some object will be equal to its change in kinetic energy, K final minus K initial, where the kinetic energy is just 1/2 mv squared, as you said. Okay, however, if I can just keep increasing v, then that suggests that K could be infinite. Right? If V can be infinitely large, infinite infinitely large speed, then I have an infinite kinetic energy. There is not infinite energy in the universe. I know, we're getting into like philosophical territory, right? But you cannot have infinite kinetic energy, right? Likewise, when we think about momentum, we can think about it like this. The sum of the external forces multiplied by some change in time gives me a change in momentum, which is P final minus P initial. And these are, of course, vectors. This is impulse, which is a change in momentum, right? And P, as you said, is M times V. This also suggests P could be infinite if, again, we have some infinite velocity. But that is not the case. So we can't just arbitrarily keep increasing the speed or the velocity of an object with mass. And we're going to see that in just a second. So let's introduce, and this is just for more compact notation. So make our equations a little bit simpler. Gamma, which is equal to 1 over the square root of 1 minus v squared over c squared, which is a factor we've seen before in time dilation. So this is relativistic gamma, that's the lowercase gamma, right? So v in this case is the speed of some particle, and then c is speed of light in a vacuum, as usual. So I want to talk about how gamma works for just a second before we move on and write these expressions for kinetic energy and momentum. V is always either 0 or some positive value. That's just the speed, right? The speed of the particle. So it's either 0 or some positive value. If it's 0, gamma is just 1, because I have square root of 1 minus 0 in the denominator. So that just becomes square root of 1 in the denominator, so I just have 1 over 1. So gamma is 1 for v equal to 0, right? For any other v, so for any other larger v, then gamma is larger than 1, because this denominator becomes smaller than 1. So for instance, we did an example previously with the arrow traveling through the box, or being contained within the box. If it's traveling at 6/10 of the speed of light, then this denominator becomes 1 minus 0.36, which is 0.64. Square root of that is 0.8. And so I have 1 over 0.8, which is 1.25. So it gets larger than 1. The closer you get to c, the closer gamma gets to infinity. Right? Because if I actually travel at speed of light c, I have c squared over c squared, which is 1, so I have 1 minus 1, and the square root, I have the square root of 0. And I have 1 over 0, which is infinite. Okay? So as v gets larger, relativistic gamma gets larger. So as v approaches c, v squared over c squared approaches 1. So gamma approaches infinity. When v is equal to 0, v squared over c squared is equal to 0, and gamma is equal to 1. So we just talked about those possibilities. So we're not going to do a derivation for this, but in relativity, kinetic energy becomes gamma minus 1 times m times c squared. So that's interesting because that's a little bit different than the expression that we have up here, 1/2 mv squared. Instead, we have gamma minus 1 times m times the speed of light squared in relativistic kinetic energy. And momentum in relativity is just gamma times m times v. much less than c, these expressions reduce to 1/2 mv squared and mv. But if I start to travel at something close to the speed of light, then it starts to diverge from 1/2 mv and mv. And let me show you how that works in a plot. Okay, so on these plots, you have Newtonian or classical kinetic energy and Newtonian or classical momentum as the red lines. Okay, so that's how kinetic energy behaves for classical physics. And then the blue lines are how it behaves relativistically, or in the relativistic formulation. K is equal to gamma minus 1 mc for kinetic energy, and P is equal to gamma times mv for momentum. And what you notice is that when we're at slow speeds, 0 is all the way over here on the left. We're at close to 0, or less than a quarter of the speed of light. They're about the same. They're basically the same value. But once you get past, say, a quarter of the speed of light, when you're getting up to half the speed of light, or at 75% of the speed of light, 0.75 c, then you have a big difference between classical kinetic energy and classical momentum and relativistic kinetic energy and relativistic momentum. Now remember what we said. We said that as V approaches C, then gamma approaches infinity, right? So in the case of kinetic energy, I'm approaching infinity minus 1 times mc squared. Have you ever, said, what's infinity minus 1? It's still infinity, right? Basically. So infinity minus 1 is basically still infinity. So my kinetic energy is going to infinity as I approach the speed of light. And the same thing happens with momentum because it's gamma times mv. So your momentum becomes infinite as you approach the speed of light. And this is why we can't travel at the speed of light. So you're asking before, does time stop if you travel at the speed of light? Well, theoretically, yes. But we can't travel that fast because we have to keep accelerating. We have to keep injecting more and more energy in order to travel up to the speed of light. Okay, let me ask you a quick question. I'll just give you a minute and a half for this one. Most people got this one. You got about 30 seconds left. Check with your neighbors just in case you're unsure. Seconds. All right, we're going to stop it there. The correct answer was an infinite amount of energy. Right? So this goes back to the plot that we just saw on the previous slide. Right? I can go from 0.8 C up to 0.9 C, that takes a finite amount of energy. But to go from 0.9 C up to C, it takes an infinite amount of energy. It seems strange, but that's the way that this function works, right? So what that means really is, again, we can't reach, we can't stop time compared to some other observer by traveling at the speed of light, because we can't ever reach the speed of light. We have mass, right? We would need an infinite amount of energy to accelerate up to the speed of light. So you may have noticed in all of the examples that we've given you previously, apart from the laser traveling at sea, which is light, right? All of the spaceships and people and things like that that are moving, they've all been traveling at something less than the speed of light, right? At 0.8 C or 0.745 C or 0.5 C, right? Because that would technically be possible according to special relativity. But you cannot accelerate up to the speed of light, regardless of what Star Wars or whatever, other science fiction movie you want to pick says. Cannot be done. Okay. So speed of light is your speed limit for the universe. There's another aspect of this. So, before we move on, I just wanted to write, this cannot be done. Oops, excuse me, off the screen. Objects with mass cannot reach speed c. There's another implication of this, though, this change that we have to kinetic energy that maybe isn't obvious, but there is an implication that this change to kinetic energy, or this change to the way that we've described energy and momentum, is that objects at rest also have an energy. And so there is rest energy as well. So, because we have to conserve energy in all inertial frames, particles at rest must have an energy. And that energy, we're going to call it E0, and we're going to call that our rest energy. And that's equal to the mass of the object times c squared. Now, I bet you've seen this equation before, right? What this is saying is that mass can be converted into energy. Or the other way around, energy can be converted into mass. So, in physics, there is kind of an equivalence between mass and energy, and there's this translation between the two. This is what's responsible for the fact that the sun is shining today. When you're outside, the energy that's coming from the sun initially starts as nuclear fusion in the core of the sun. The temperature and pressure at the center of the sun are high enough that they can overcome the electrostatic repulsion of two protons. So two protons, right, are two positive charges. They exert force that repels each other. You learned that at the very beginning of this class, right? If I get them close enough together, though, I can overcome that electrostatic repulsion, and they bond together. That's nuclear fusion. It's a little bit more complicated than that. But in the process of doing that, we can convert hydrogen into helium. You have to do a couple more steps to get a helium-4 nucleus with two protons and two neutrons. But you go from 4 protons to a helium-4 nucleus, 2 protons and 2 neutrons. And the helium-4 nucleus has a little bit less mass than the 4 protons did to begin with. What happens to that mass? So that mass is converted into energy. It tunnels its way out of the sun, which takes maybe a couple 100,000 years, and then it radiates from the surface and then reaches Earth. Okay? In the form of sunlight. There you go. So we're converting a little bit of mass, or a lot of mass, at all times in the core of the sun into energy. And you can do it the other way around as well. You can also convert energy back into mass in some scenarios. Okay. So what this says then, and this is also something that Einstein concluded. Rest energy says that mass is just a different manifestation of the energy. And most starlight, not all starlight, but most starlight comes from hydrogen plus hydrogen being converted into helium via fusion. There are other fusion processes that happen in stars, but we're not going to get into the details of that. If you want to learn about that, you've got to become a physics major. You've got to take calculus-based version of this course and physics 1, sorry. Then you've got to take modern physics. Then you can take my stellar astrophysics class about how the interiors of stars work. But that's what's going on. And like I said, the four protons that end up making the helium-4 nucleus have a little bit more mass than the helium nucleus, and that's where the energy comes from. Okay. So far, we've mostly talked about inertial frames, where someone is traveling at a constant speed. Now, we did have some exceptions, like the twin paradox, where twin 2 spent some time in an accelerating reference frame. And as a result, she ended up younger than twin 1 when she took that trip out and back. Right? Understanding accelerating reference frames requires a different type of relativity. Rather than special relativity, which deals with time dilation and length contraction, we need general relativity. General relativity relies upon the principle of equivalence, which says that a gravitational field is equivalent to an accelerated frame of reference in the absence of gravity. And I've run out of space on this page, but I will illustrate that on the next page instead. So here's the example to illustrate what we mean by the principle of equivalence. Here's a box. The box is windowless and it's soundproof, so the person in the box cannot hear, cannot see anything from the outside, and they only have a ball. And so this person is going to throw the ball horizontally. So they toss this ball horizontally, and then what happens? The ball travels along a parabolic path to the floor. You studied physics 1, right? Remember the projectile motion. If I throw something horizontally, so, let's just grab a pen over here. If I throw this pen horizontally, it's going to follow a parabolic path to the floor because of the fact that Earth's gravity is causing it to accelerate in the y direction, while in the x direction it has constant velocity. You probably remember that from from projectile motion in physics 1. All right, possibilities. I'm only drawing stick figures because I gotta, not have class take forever. All right, possibilities. The box sits on Earth in its gravitational field. So in other words, acceleration in the y direction is minus little g, right? And that's what's responsible for the ball taking a path to the ground. Right? Second possibility. Instead, the box is attached to a rocket. And the rocket is accelerating at A is equal to G with constant acceleration. So that's also a possibility, right? This is the observation that you did in this windowless, soundproof box. You can't see what's on the outside, you can't hear anything. There's no vibrations, nothing. You have air inside the box, okay, but it's perfectly sealed. I know, we'd have to add some more technical stuff to keep you alive inside the box. But either one of these is possible. You can either be sitting on Earth or accelerating, right? So the point is that this person in the box, the observer, cannot tell the difference between these two. That's a little troubling. All right. So mathematics and general relativity are very challenging. So I'm only going to describe some of its predictions qualitatively. Gravity, or mass, bends light. And I'm going to show you an example of that. Or you can say space itself is curved by mass, right? These are two different ways of kind of saying the same thing. And then lastly, strong gravity or proximity to a large mass slows time. And remember, we talked about how in the twin paradox, the twin that accelerates experiences time passing slower. Well, we just said that an accelerating reference frame is equivalent to being in a gravitational field. So if you're in a gravitational field, then time is going to pass more slowly for you if it's very strong gravity. And I'll give you an example of that as well in just a little bit. But first I want to show you what I mean by gravity bends light, or space itself is curved by mass. If you think about space as a rubber sheet, a little bit like this. You can turn off one of the lights for this. So if you think about space as a rubber sheet, and if there's nothing on that space, then the sheet is perfectly, everything's at right angles and it's perfectly flat. But if I put some bowling ball and maybe a tennis ball and then maybe some other lighter ball, a golf ball on that sheet, then they will depress the sheet by the amount based on their mass, right? The bowling ball, which maybe is the yellow one, is depressing the sheet by a larger amount, so it's curving space by a larger amount. Now this is really happening in 3 dimensions, not 2 dimensions like a sheet. So this is an analogy. But what this does is it curves the path of light. So let's say I have a star that is over here. And let's say that the yellow ball is the sun and the red ball is the earth. And so from the earth, I see this star. But the path that the light takes from the star to me is curved when it passes by the sun, because the sun is curving space-time near the sun. The light path travels at a slightly different direction, and it actually makes a curve through space. This happens, called gravitational lensing. Now, I've exaggerated it on this slide, but that's actually what occurs. And so you see the star as though it were there, but its actual location is over here because the light path has changed. You imagine light always just traveling in a straight line, but because of the curvature of space-time, it can actually change direction. All right, let me give you another example of that. So here we are on Earth, and if I have a galaxy cluster at some very large distance from us, Earth is not shown in scale, right? The galaxy cluster has enough mass that it can curve the space near it, which is shown by our sheet underneath it being depressed in the same way that the bowling ball or the sun did. And the path of light from some galaxy that's even more distant than the galaxy cluster can be curved around this galaxy cluster and then reach the Earth. And this is a lot like a converging lens. And so that's why this is called gravitational lensing. This is using the mass of gigantic galaxy clusters to lens the light from a distant galaxy, which both, it produces an image of the galaxy in the same way that we produced images with a converging lens. It magnifies that galaxy, and so this is using nature like a telescope, basically. And so here's an example. So this is a galaxy cluster. I'm forgetting the name off the top of my head, but I think it's PHY2054 something. And there is a very large elliptical galaxy, which is this very bright yellow fuzzy spot in the center. There's also some spiral galaxies in this image as well. I think this is a spiral galaxy, this is a spiral galaxy, but this is a large elliptical galaxy, so it's shaped more like a ball than the disk where a spiral galaxy is. And then there are galaxies that are behind this cluster that are lensed by the cluster. So you see these little arcs of light, right? Those are distant galaxies behind this cluster that are being lensed by the cluster itself. And so you can then take a look at these even more distant galaxies by virtue of the gravitational lensing that's occurring. All right, let me give you another example. Another aspect of this is that because an object will curve space-time, if you have two objects that are orbiting around each other that have very significant curvatures to the space-time due to their very high densities and very high masses, like for instance, two black holes orbiting each other, then they will cause ripples in space-time that propagate outwards, gravitational waves. And so let me show you an illustration of that happening, right? So there are merger events that happen in the universe where you have black hole orbiting another black hole, maybe slightly different masses. So before the merger, you notice that the two black holes are different sizes, right? But as they get closer and closer, they will spin faster and faster, and then eventually merge, and that produces a burst of gravitational waves, which is detectable on Earth. Okay? And this has only been, this is relatively new. The first gravitational wave detection was in 2015, during your lifetime. Yes.
What happens when gravitational waves
It is an extremely faint effect that is very difficult to detect. So I'm going to show you approximately how to detect that. I'm going to show you a video about that, but probably not till next time because we're going to run out of time. But I don't have time to show you the video. I'll show it to you again in next class next week. But this is the detector for detecting the gravitational wave, or one of the detectors. There's multiple. There's more than one of these now. But this is in Hanford, Washington, State Washington, and it's two laser beams that travel along these two very long arms. There's really just one laser beam, I should say. So there's one laser beam that's produced at this building here at the bottom of the slide. And then it's split into two, and it travels along these two paths. Okay? And then it reflects off of a mirror at the very ends of these two paths, and then comes back to this building. And then when it comes back to this building, there's interference. It either overlaps with peak over trough, destructive interference, or peak over peak, constructive interference, based on the two path lengths. When a gravitational wave passes by this detector, it will compress one length of this detector, and it will expand the other length. And so by changing the length a little bit along one direction and changing the length a little bit along the other direction, you will get a change in constructive or destructive interference of the two light beams that are recombining with this building. And that will tell you that the gravitational wave is passing by. Now, the length change is close to the width of the proton. It's very, very small. So even though the length of these arms is 4 kilometers, or something like 2.5 miles, it's a change in length of about the width of the proton. So it's extremely difficult to detect. The reason that this is in this sort of remote area where there's no other building is because you want to be as far away from people and roads and all sorts of things like that as possible, because any small little vibration can mess up your detection. Okay? So they also put these in geologically stable areas where you're unlikely to have an earthquake or unlikely to have a lot of little tremors, because that could also set off your detector. So I'll show you a video about this next time, produced by the New York Times, when the first detection was announced back in 2016. The detection happened in 2015. It was announced in 2016. We'll come back to that next time. See you on Monday.